So today's a very special year for Apache Spark. Spark 3.0 is out, but it's also 10 years since the first open source release of Spark. So I want to talk to you today about what got us here with the open source project and what did we learn in the process that we're using to contribute to Apache Spark development in the future. And to do that, I'll start by telling you my story with big data, how I got into this space when I started my PhD at UC Berkeley. So I started my PhD in 2007, and I was very interested in distributed systems. I had actually been working on peer-to-peer networks before this, but I wanted to try doing something different. And as I looked around at what's happening in the industry, I got very excited about data center scale computing. These large web companies were starting to do computations on thousands of machines and store petabytes of data and do interesting things with them. And I wanted to learn more about these, and so I actually worked with some of the big data teams at Yahoo and Facebook early on. And in working with these, I realized that there's a lot of potential for this technology beyond web companies. I thought this would be very useful for scientific data sets, industrial data sets, many other things. But it was also very clear that working with them, these technologies were too hard to use for anyone who was not at a large web company. In particular, all the data pipelines to use these technologies had to be written by professional software engineers. And also all the technologies were really focused on batch processing. There was no support for interactive queries, which is very important in data analysis, no support for machine learning and advanced algorithms. And when I came back to Berkeley after spending some time working on these, I also found that there were local research groups who wanted a more scalable engine for machine learning in particular. So I thought this was a great opportunity to try building something in this space. And in particular, I worked early on with Lester Mackey, who was one of the top machine learning students at Berkeley in my year, and who was on a team for the Netflix prize competition, this $1 million competition to improve Netflix's algorithm. And so by seeing the kind of applications that he wanted to run, I started to design a programming model that would make it possible for people like Lester to develop these applications. And I started working on the Spark engine in 2009. Now, once I started the work, the feedback on it was great. These machine learning researchers at Berkeley were actually using it. And so we decided to open source the project in 2010. And this is what the initial version of it looked like. So it was a very small open source project, really just focused on MapReduce style computing with a cleaner and faster API. But the exciting thing is that within 2 months of us open sourcing it, we started getting pull requests from other community members. So there were really people picking this up, trying to use this very early project and doing interesting things with it. And so we spent the next 2 years working with early users in the Bay Area. I spent a lot of time actually visiting these companies and organizing meetups and trying to make this a great platform for large-scale data processing. And in working with these early users, we were blown away by some of the early use cases. People were doing things that we as researchers had never anticipated, and we thought that there's the potential to do a lot more here. So, for example, some of the early users were powering interactive operational apps like a user interface using Spark on the backend. For example, there was a group of neuroscientists at Janelia Farm that were monitoring data from the brains of animals and other sensors in real time while they're running neuroscience experiments and building that up using Spark. That was something we had never anticipated. It's obviously very cool to be able to build these operational apps for exploring large data sets. Another interesting group was from this startup company, Quantifind, that had built a product for its customers to analyze social media and other data sources. And they actually were using Spark to update data sets in memory and implement streaming computation. This was before we added a streaming engine to Spark. So they had just built streaming computation on this platform. And finally, there were groups in industry, for example, Yahoo's data warehousing group that were running SQL queries over Spark or R data science workloads and other workloads. And they were opening up the Spark engines to tens or even hundreds of more users than we initially had been targeting. So based on these use cases and what Spark was able to do for these companies, we spent the next few years really working on expanding access to Spark, making sure that anyone who works with data can somehow connect to this engine and be able to run computations at scale. And there were three major efforts there. The first one was around programming languages. So we developed Python, R, and SQL interfaces to Spark that today are by far the most popular ways of using the engine. The second was around libraries. We wanted to have great built-in libraries for machine learning, graphs, and stream processing, and these provide a lot of the value of the platform today. And finally, we also got a lot of feedback on the API, what users found difficult, for example, how to set up map and reduce and other operators to do a distributed computation. And we decided to make this big change to the high-level API called data frames, which runs most of the APIs in Spark on top of the Spark SQL engine. So you get the same kind of optimizations and query planning that a SQL engine will do, but in these easy-to-use, programming language interfaces. And that quickly became the dominant way to use Apache Spark. So if you look at Apache Spark today, these changes have all had a huge impact on the project. Let's start with support for Python. Among the users of interactive notebooks at Databricks, where we can measure this, 68 of the commands coming into the platform are in Python. This is more than 6 times the amount of Scala. It's by far the most widely used programming language on Databricks today, and it means a wide range of software developers are able to connect their code to Spark and execute it at scale. Interestingly, the next most common language in notebooks is SQL. There's also a similar amount of commands to the total that we have in notebooks is just coming in through SQL connectors directly. So that's also very widely used. Next thing is SQL. So even when developers are using Python or Scala, about 90% of the Spark API calls are actually running on Spark SQL through these data frame APIs and other APIs, which means they benefit from all the optimizations in the SQL engine. And just on Databricks alone, we're seeing exabytes of data queried per day using Spark SQL. As a result, the community has invested a lot in the Spark SQL engine and making it, one of the best open source SQL engines on the planet. So for example, this plot here shows the improvement in performance on the TPC-DS benchmark, the leading benchmark for data warehousing workloads. And you can see with Spark 3.0, Spark is now running 2 times faster than the previous version, and also about 1.5 times faster than Presto, very highly regarded SQL engine for large-scale data sets. And another exciting piece of news that happened with SQL this year is that earlier this year, Alibaba set a new benchmark for the TPC-DS, a new record for the TPC-DS benchmark using the Spark SQL engine to exceed, the cost performance of all the other engines that have been submitted to this benchmark. So it's really the basis of very, very efficient and powerful SQL engines today. And the final one I want to talk about is streaming. Just on Databricks alone, we see about 5 trillion records per day processed with structured streaming, which makes it super easy to just take a data frame or SQL computation and turn it into a streaming one. And this number has been growing by close to a factor of 4 year over year. So we're seeing very fast adoption of this high-level streaming API. Okay, so given these changes of the project, what are the major lessons that we learned? For me, at least, there were 2 big lessons. The first one is to focus on ease of use, prioritize that for both data exploration and production. We found that a lot of the applications that people built quickly became these operational apps or streaming apps or repeated, reports, and we wanted to add a lot of features into the engine to make it easy for these to keep going and to tell you, if something changes or something breaks in a way that's easy to fix. So a lot of the work in Spark now is to make that super easy. The second big lessons we had was to really design the system around APIs that enable software development best practices and integrate with the broad ecosystem. So we designed all the APIs in Spark so that they fit into standard programming environments like Python and Java, and so that you can use best practices like composition of libraries into an application, testability, and modularity. And you can build packages that a user in your company can safely use to do a computation computation or have this wide open source community around them. And this is something where we've done a lot of improvements over time as well. Okay. So given these lessons, what's happening in Apache Spark 3.0? This is our largest release yet with over 3,000 patches to the community, and it's actually designed to be easy to switch to from Spark 2. So we definitely encourage you to check it out and switch to it when you can. This chart here shows where the patches have gone, and you can actually see almost half the patches are in the Spark SQL engine, both for SQL support itself and because it's the underlying engine for all these data frame API calls. So this is the most active piece of development, but there's of course a lot else going on as well. So I just want to highlight a few of the features that I'm excited about, focusing specifically on SQL and Python, but of course, there's quite a bit of other stuff going on in 3.0 as well. And I'm going to start with a major change to the Spark SQL engine, the largest change in recent years, which is called adaptive query execution. So this is a change where the engine can actually update the execution plan for computation at runtime based on observed properties of the data. For example, it can automatically tune the number of reducers when doing an aggregation or the join algorithms, or it can even adapt the skew in the data to plan the computation as it's going. And this makes it much easier to run Spark because you don't need to configure these things in advance. It will actually adapt and optimize based on your data, and also leads to better performance in many cases. So to give you a sense of how it works, let's look at a simple example of setting the number of reducers. We found that today about 60% of clusters, the users tune the number of reducers in them. So that's a lot of manual configuration that we want to eliminate and automate. And so with AQE, what happens is after Spark runs the initial phase of an aggregation, it actually observes the result size. You can have some number of partitions there, and it can set a different number of partitions for the reduce. For example, coalesce everything down to 5 partitions and optimize it for the best performance based on what kind of data came out of that aggregation. Now, even more interesting things happen with joins and more complicated operators. For example, when you're joining two tables, even if you have high quality statistics about the data, it's hard to know how many records will end up before the join. And using AQE, Spark can actually observe this after the initial stages of the join have happened, and then choose the join algorithm that best optimizes performance downstream. And in fact, it can adapt both to the size of the data and to the skew around different keys. So you don't have to worry about treating skewed keys in a special way anymore. And these results in really big speed ups on SQL workloads. So for example, on TPCDS queries, we've seen up to a factor of 8 speed up with AQE. And even better, it means you can actually run Spark on a lot of data sets even without pre-computing statistics and get great performance because it discovers the statistics as you go along. Okay. That's just one of the changes that affects both SQL usability and performance. There's quite a bit more. So on the performance side, we have dynamic partition pruning, query compile time speedups, and optimizer hints. And as I said earlier, these have led to a 2x reduction in execution time for TPCDS and a lot of improvements on real workloads. And finally, there's been a big effort in 3.0 around SQL compatibility, in particular an ANSI SQL dialect that follows the standard SQL convention in many areas of the language, and that makes it very easy to port in workloads from other SQL systems. And this is one of the areas that we're continuing to invest in, but we've made significant strides in 3.0. Okay, so that's a bit about SQL. The other thing that I wanted to highlight is around Python. So we've done quite a bit of work on both Python usability and performance. For usability, we've made it much easier to define Pandas user-defined functions using type hints in Python, which let you specify the format of data you expect. So in Spark, it's easy to make a function that takes in batches of data as Pandas series or data frames, for example, or even as an iterator of series, and you can just specify these with type hints. For comparison, the previous API required you to write a lot of boilerplate code in order to say what kind of input your function expects, and that was very error prone. So now that can go away, and it's super straightforward to define and use these functions. There's also been a lot of work on performance using Apache Arrow. We're seeing about 20 to 25% speedups in Python UDF performance using the latest enhancements in Apache Arrow, and also up to a 40 times speedup in Spark R by using Arrow to exchange data between R and Spark. And these are all transparent to the end user. You just upgrade and you get these speedups. And we have quite a few new APIs for combining Pandas with Spark as well. And finally, there are features throughout the engine, including a new structured streaming UI for monitoring computations, a way to define custom observable metrics about your data that you want to check in streaming jobs, a SQL reference guide, and a powerful new API for data sources. So if you want to learn more about Apache Spark 3.0, I invite you to check out Shao Li's talk at this summit and many of the talks on these individual features. And the Spark project itself is not the only place where things are happening. There's actually a broad community around it, and I wanted to highlight some of the changes. So at Databricks last year, we released Koalas, which is a Pandas API that can run directly over Spark to make it very easy to port workloads. And that's evolved a lot in this year. I'll talk about it. Of course, there's Delta Lake for reliable table storage. And we've also done quite a bit of work to add Spark as a scale-out backend in popular libraries, including scikit-learn, hyperopt, and joblib. So if you use these for machine learning, you can just scale out your jobs on a Spark cluster. We're also collaborating with Regeneron to develop GLOW, a widely used library for large-scale genomics. And NVIDIA has been developing Rapids, which provides a wide range of data science and machine learning algorithms that you can call from Spark that use GPU acceleration and really speeds up these workloads. And finally, we've also done a lot of work on Databricks on improving connectivity with both commercial and open source visualization tools so that users can build interactive dashboards using Spark as the backend. So I'll just dive into some of the changes in Koalas specifically. If you're not familiar with Koalas, it's an implementation of the Pandas API over Spark to make it very easy to port data science code in this really popular library. We launched it actually a year ago at Spark AI Summit, and it's already up to 850,000 downloads per month, which is about a fifth the total downloads of PySpark. So we're really excited with how the community has adopted this library. And we're investing quite a bit more into Koalas. And at this event, we're actually excited to announce Koalas version 1.0. This new release has close to 80% of the API coverage of Pandas. It's also quite a bit faster thanks to the improvements in Spark 3.0, and it supports a lot of features that were missing before, including missing values, NAs, and in-place updates. And it's also got faster distributed index type. It's very easy to install Koalas and PyPy and get started. And if you're a Pandas user, we believe this is the easiest way to migrate your workloads to Spark. So that's enough of me talking. We also like to show you demos of all these new things. And I'm really excited to invite Brooke, Wenig, the machine learning practice lead at Databricks, to give you demos of the new features in Koalas and Spark 3.0.
Hi, everyone. These are some crazy times. And while we're all still social distancing, many of us are staying at home trying to figure out, what are we going to cook for dinner tonight? I know my whole SF office has gone through the banana bread and sourdough craze, but now we need some new recipes to impress our coworkers with on our food Slack channel. In particular, we need to find a recipe for Matei. Matei is a very busy person who loves to optimize everything. Given the increase of people contributing recipes, we now have millions of recipes that we need to analyze in a scalable manner so that Matei can make a data-driven decision on what he's going to prepare tonight. Along the way, we'll explore some new features in Spark 3.0 and Koalas. Let's get going. Like any data scientist, I'm going to start off with some exploratory data analysis with Pandas. Pandas is a great way to get started with exploring your data because it's simple to use, has great documentation, and a fantastic community. Let's go ahead and visualize this subset of our data. You can see here that our recipes data contains the name of the recipe, when it was contributed, nutrition, ingredients, etc. However, we don't just have one file, we have a whole directory of Parquet files we need to read in. So let's go ahead and load in our entire data set with Pandas. Unfortunately though, Pandas wasn't prepared to handle the rising recipe count. So if we allow this query to continue on, it'll crash trying to load in 30 gigabytes of data onto a single machine. Let's instead cancel it. Now let's use Koalas to load in our data set instead. Koalas provides the pandas-like syntax and features that you love, combined with the scalability of Apache Spark. To load in our dataset with Koalas, we simply replace any of the PD logic with KS for Koalas. And now you can see just how quickly we can load in our entire dataset with Koalas. But let's say Matei's pretty busy tonight, and he wants to find a recipe that takes less than 30 minutes to prepare. You can see I've already written the pandas code to filter out for recipes that take less than 30 minutes, and then visualize the distribution of the number of steps these recipes take. To convert it to Koalas, I simply replace my pandas data frame with my Koalas data frame. And voila! I no longer need to downsample my data in order to visualize it. I can finally visualize big data at scale. We can see here the distribution of the number of steps. While most recipes take less than 10 steps, you can see the x-axis extends all the way out to 100. There's a universal muffin mix that takes 97 steps to prepare. Matei won't be cooking that one tonight. In addition to our recipes data, we're also interested in the ratings for those recipes. Because Koalas runs on Apache Spark under the hood, we can take advantage of the Spark SQL engine and issue SQL queries against our Koalas data frame. You'll see here that we have our ratings table. Now we want to join our ratings table with our recipes table. And you'll notice I can simply pass in the Koalas data frame with string substitution. Let's go ahead and run this query. Wow, we can see that this query took over a minute to run. Let's see how we can speed it up. I'm going to copy this query and move it down below, after I enable adaptive query execution. With adaptive query execution, it can optimize our query plan based on runtime statistics. Let's take a look at the query plan that's generated once it's enabled. I'm going to dig into the Spark UI and take a look at the associated SQL query. Here, we can see that it passed in a skew handling hint to the sort merge join based off of these runtime statistics. And as a result, this query now takes only 16 seconds for about a 4x speedup with no code changes. In addition to using Koalas to scale your pandas code, you can also leverage Spark in other ways to scale your pandas code, such as using the Pandas function APIs. We're going to use the Pandas function APIs to apply arbitrary Python code to our data frame, and in this example, we're going to apply a machine learning model. After seeing that universal muffin mix take 97 steps in 30 minutes, I'm a little bit skeptical of the time estimates for these recipes, and I want to better understand the relationship between the number of steps and ingredients with the number of minutes. As a data scientist, I built a linear regression model in our dataset using scikit-learn to predict the time that a recipe will take. Now I want to apply that model in parallel to all records of our data frame. You'll notice here just how easily I can convert our Koalas data frame to a Spark data frame. To apply our model, I'm going to use the function called map_in_pandas. Map_in_pandas accepts a function you want to apply with the return schema of that data frame. The function I want to apply is called predict. Predict accepts an iterator of pandas data frames and returns an iterator of pandas data frames. I'm then going to load in our model. If your model is very large, then there's high overhead to repeatedly load in the model over and over again for every batch in the same Python worker process. By using iterators, we can load the model only once and just apply that to batches of our data. So now let's go ahead and see how well our model performs. We can see here that the predicted minutes is pretty close to the number of minutes for some recipes. In this case, the true number of minutes is 45, we predict 46, or the true value is 35, we predict 39. But in some cases, our time estimates are a bit off. And we can actually see in the description, don't be dissuaded by the long cooking time. So Matei's decided he doesn't want to cook anything tonight, he just wants to make a smoothie with the shortest preparation time. So Matei, which recipe will you be preparing? Looks like Matei will be preparing a berry smoothie with only 4 ingredients and a grand total of 0 minutes. Wow, he's really optimizing for speed. Stay tuned for a very delicious surprise.
Wow, thanks, Brooke. That was an amazing demo, and the smoothie turned out delicious. It's great. One other announcement I wanted to make that also ties into Brooke is that we've been working to publish a new edition of Learning Spark, the popular book from O'Reilly. Brooke is one of the co-authors actually, and we're giving away a free copy of the ebook to every attendee at the summit. So we invite you to check this out if you want to learn about the new features in Spark 3.0. Okay, and then the final thing I want to end on today is what's happening next in the Apache Spark ecosystem. If we step back and look at the state of data and AI software today, it's obviously made great strides over the past 10 years, but we still think that data and AI applications are just more complex to develop than they should be. And we think that we can make that quite a bit easier, and we have a lot of ongoing efforts in open source Apache Spark to do this, building on these two lessons, ease of use in exploration and production, and APIs that connect with the standard broad software ecosystem. So I'm just going to briefly talk about three big initiatives that we are working on at Databricks for the next few versions of Spark. So the first one is what we're calling Project Zen. The goal is to greatly improve Python usability in Apache Spark. Because it is the most widely used language now, we want to make sure that Python developers have a fantastic experience that's familiar with everything else that they do in Python. And there are quite a lot of areas where we think we can improve the experience. We've called this Project Zen, by the way, after the Zen of Python, the set of principles for designing Python that have led to it being such an amazing environment today. So some of the things we're working on are better error reporting, porting some of the API changes from Koalas. We got to experiment with them there, and we think they're useful enough that we want them to just be part of Spark, improve performance, and Pythonic API design for new APIs. I'll give a few examples of what we're doing with this next. We also have a continued initiative around adaptive query execution. We've been really pleased with what it's doing so far, and we think we can cover more and more of the SQL optimizer's decisions adaptively and really dramatically reduce the amount of configuration or preparation of the data needed to get great performance with Spark. And finally, we're also continuing to push on ANSI SQL. The goal is to run unmodified queries from all the major SQL engines by having dialects that match these. And we think we've been working a lot with the community to build these, and we think it will provide a lot of benefit in Spark. Just to give you a couple of examples of the Project Zen features, one of them is around error messages. So if you run a Python computation today and you have an error on your worker process, such as dividing by 0, you get this very scary looking error trace in your terminal. Lots of stuff going on. And if you look at it closely, there's a lot of Java stuff, and maybe you can see part of the error trace is actually about the problem that happened in your Python worker, which in this case was division by 0. But it's pretty unfriendly, especially if you're just a Python developer. It's hard to see exactly what was going on. So as part of Project Zen, we're simplifying the behavior in Python of a lot of common error types, so that if it's a Python-only error or a SQL planning error, you see a very small message that lets you directly fix the problem. So you can see this has just the Python-relevant bits of that error, and you can see that there is a division by 0. Of course, this might be a bad example because if you really accept Project Zen, you will come to a much better understanding of emptiness, and you will probably never get divisions by 0 again. But it's just one example. And then the second change I want to show is a new documentation site for PySpark that's designed to make it really easy to browse through, find Python examples, and it's built on kind of the latest best practices for Python documentation. And we think this will make it easier to get started for many of our users as well. So these are some of the changes. We're really excited about what's next for Apache Spark, and we look forward to seeing what you do with it.